My name is Stuart Kauffman, and we're going to talk about very large transitions in the evolution of how we think of the world. Before we go on to consider Kantian holds making their worlds with one another, which we surely do, I'd like to take us back to think again about the origin of life. I must stress that nobody knows how life in fact started. Many people are working on it. There's a reasonable chance that we will find ways of constructing life in the next 30 or 40 years. So I'm going to carry us forward on one pathway that I like and I think is testable. Let me go back to the emergence of collectively autocatalytic sets, or rafts, of small molecules of the kind that Joanna Xavier led us to find. I will call it the Joanna set. She's really quite wonderful. So she found, with Bill Martin and the others, in archaea and bacteria from more than 2 billion years ago, a collectively autocatalytic set of small organic molecules with no polymers that's really there. It's a molecular fossil from before oxygen in the atmosphere. The autocatalytic set, which has things in it like ferrosulfate and so on, not only makes a linked connection of reactions among 1,500 small molecules, in so doing, that set makes amino acids and makes the nucleotides A, C, T, and G, and U that go into making proteins for the amino acids, and the nucleotides that go into RNA and DNA. We have no polymers yet. How might we get polymers? The same idea of collectively autocatalytic sets applies to polymers. I have thought for years about proteins, and I told you Gonan Ashkenazi as a set of 9 proteins that mutually catalyze one another's formation, or RNA, and I've told you that RNA autocatalytic sets have been made and protein autocatalytic sets have made experimentally, and one can imagine a system that has mixed RNA and protein. I'm going to sketch an image from David Deamer that I like a lot. The early Earth has 2 plausible sites for the origin of life. Deep underwater hot vents, which is a favorite of some, and others, like my friend David Deamer, like the idea that early life started in pools, hydrothermal pools on dry land near volcanoes with water flowing in and out to the sea that go through wet and dry cycles. So I need to tell you about something called liposomes. They're really fun. They're easy to make. Take cholesterol, just cholesterol, and put it in water. And cholesterol can form a 2-surfaced structure called a membrane, just like your cell membranes. Cholesterol is a molecule that has one end that likes water and the other end doesn't. In the presence of water, what cholesterol does is it makes a bilipid layer with the water-loving molecules on the outside of the 2 layers and the water-hating hydrophobic parts of the molecules on the inside. And it forms little bubbles that are about 2 or 3 microns across, called liposomes. So everybody who's thought about the origin of life realizes that liposomes look pretty much like cell membranes, and that they would have formed very easily on the early Earth with myriad molecules present. So Deamer's scenario with Bruce Damer is a hydrothermal vent that goes through wet-dry cycles when the sun comes, and they want to imagine that inside of these liposomes are some more or less random combinations of peptides or RNA sequences. And I now need to tell you of an amazing reaction called the plastine reaction, done in 1932. I happen to know the names. It's Wassenaar and Borsuk, because I learned it at some point. So what they did is they took, in effect, hamburger, and they used an enzyme that breaks down hamburger, which is long chains of amino acids, into little ones. And they left the enzyme in, but it's going to turn out not to matter. When they put them in a solution that they dehydrated, they're taking away water, what happens is that the little peptides glue together to form bigger peptides. And the reason is, when a peptide bond forms, it releases a water molecule, and if you take away the water, the reaction tends to run faster. As the chemists say, it runs to the right. So if you take away the water, you make longer polymers. If you add water back, the longer polymers break down to shorter polymers. And I made use of that in my own book in 93, Origins of Order. So the image that Deamer and Damer have is of a lagoon with these liposomes, as they're called, the membranous things, with more or less a random assignment of a peptide or RNA polymers going through a wet-dry cycle. Well, drying is in effect adding energy to the system, and their images, you get a shuffling of little peptides that go to bigger ones and bigger ones that go to littler ones when you add water. And I add to that, fine, now an autocatalytic peptide set emerges. So let's imagine that. So let's suppose that it's pretty easy to form peptide autocatalytic sets. We're trying to do some experiments now to do it. It may be the case that a man named Lee Cronin has done it in Glasgow. He tells me that he's done it, but he hasn't published it yet. So let's suppose that it's relatively easy to get peptide autocatalytic sets. Well, if that's true, and you have a small molecule autocatalytic set, what one would hope would happen is that the peptide autocatalytic set that forms constitute peptides that are enzymes or catalysts that catalyze the very reactions in the small molecule autocatalytic set. Because in you make proteins that catalyze the reactions in your intermediate metabolism. That's not crazy if there's a Joanna set making amino acids and nucleotides, and it can co-evolve with peptide autocatalytic sets, where the autocatalytic peptide sets can change and evolve. You would think that such a set might evolve to a peptide autocatalytic set that makes use of and instantiates catalyzes the very reactions that are the small molecule metabolisms that give rise to the building blocks needed to make the autocatalytic peptide set or RNA set. So let's imagine that works. Then we've got a first constraint closure for small molecule autocatalytic sets, a second constraint closure to a world of polymers, peptide or RNA will do, that catalyzes the reactions inside of a dividing liposome, we may hope. We're on our way to a protocell. This is superb. We need a major next step. And actually we need two, but I'll tell you first about one. You all know that you have DNA and RNA and so on inside of you. The way DNA in fact replicates in you is pretty much the way Watson and Crick said. There's the Watson side of the DNA molecule and the Crick strand, and they're tied together by Watson-Crick pairings of A's and T's and C's and G's. And what happens in your cell is that an enzyme unzips the double strand, and the Watson old strand is used to synthesize a new Crick strand, and the old Crick strand is used to synthesize a new Watson strand. And the protein that does that is called a polymerase, and this process is called template replication, which is the dream of the RNA world. Well, we have to get there. So we don't know how, but here's some ideas that I'm considering with some other friends, Niles Lehman and others. We know that short 10 nucleotide long DNA pieces, double-stranded DNA or RNA, can stack end to end and make long stacks. Well, that's nice. Suppose that happens, and because that's happening, some protein begins to evolve that can copy not 10 nucleotides, but maybe 15 or 20 nucleotides. It's on the way to becoming a polymerase. That's not impossible. Some other people in Europe have evolved an RNA molecule that is able to template replicate another RNA molecule for about 200 nucleotides. So one can begin to imagine starting with a Joanna set, getting to a polymer set, and then evolving the capacity for template replication. A third constraint closure, we need a fourth, and that is the magic of DNA encoding for proteins. So you probably know that the DNA molecule has a genetic code. 3 adjacent nucleotides like CCC or GGG or GAC each code for a specific amino acid. The way it works in your cell is your cells make 20 different kinds of small RNA molecules called transfer RNA. Each transfer RNA has, roughly speaking, a triplet that binds to its appropriate code triplet. If the code is CCC, the transfer RNA makes a GGG that can recognize CCC and binds to it. The same transfer RNA has a second site, and the second site is a place where a specific amino acid, the one that is appropriate for the code, whatever I said, GGG, is attached to the transfer RNA. So each of the 20 transfer RNAs has attached to it the right amino acid, and then they are lined up next to one another, and they are made into a protein by the ribosome. The magic is, how does the right amino acid get to the appropriate transfer RNA? And the amazing thing is, your genes code for a protein, actually for 20 different proteins called amino acyl synthetases, each one of which specifically loads the right transfer RNA to the with the right amino acid. So the code instantiates itself in a self-reflexive way, and we don't know how the code arose. Some friends of mine and colleagues of mine are working very hard on it, Peter Wills and his colleagues in New Zealand, and the idea is that's another form of autocatalytic set in which RNA and peptides co-evolve with some sort of RNA autocatalytic set co-evolves in some way with some perhaps peptide autocatalytic set, and they manage to co-evolve together to another Kantian whole, or parts of a Kantian whole, that's an autocatalytic set that instantiates coding. Nobody knows that, but that's a hope. So if we've gotten that far with 4 constraint closures, we can dream that we get to something like small molecules, a metabolism, polymers like DNA and RNA and proteins, something like template replication, and something like the code, the last of the enormous mysteries. So let's just jump and say at least we can imagine it. And much of this is testable, and people are working on it, and we'll hope we know. So hold that. Now we've got something like the modern bacterium. Well, let's think about this modern bacterium. It really is a Kantian whole. A bacterium like E. coli in your gut has about 3,000 genes coding for 3,000 different proteins. You have about 23,000 genes coding for 23,000 proteins, and roughly an equal number of sequences that code for RNA that never gets made into proteins. So just think of the bacterial cell. It's got 3,000 kinds of proteins doing all kinds of things. And let's talk about your cell now. You've got about 50,000 polymers. They're actual physical structures. And when you pause to understand what's going on in a cell, it's amazing. It is not a soup of it's not coffee with a little milk stirred into it. Some molecules make fibrils that run across the cell. On the fibrils, life has evolved little molecular motors that walk along the fibril and carry a cargo from one spot to another in the cell, like little trolley cars. Your cells have pores in the membrane that open and close to admit, roughly speaking, food and keep out poison, to pump out water from the inside so they don't explode by having too much water in them. They osmoregulate. They discriminate hundreds of kinds of things on the outside world and bring them in. And they act in their world. If you've never seen it, watch a movie of an amoeba swimming. It's magic. So this is all physics and chemistry. Now, I want to convey another thought that is a strange one. The set of 50,000 polymers in you, and the small molecules, and the lipid membranes, and the fibrils, and so on, are each like the engine block. Each is a real three-dimensional physical object. Remember that the function of your heart is to pump blood, not to have water in your pericardial sac and make heart sounds. The function is always a subset of the causal consequences. We have no idea right now the myriad causal consequences of 50,000 different polymers and small molecules and membranes that are the way that the system organizes and functions, in which the causal consequence that sustains the Kantian whole is the function of that part. It's not true that we have no idea. 50 years of intense molecular biology has revealed an awful lot of it. So we come to know that. Please have that in mind when we think about a cell. So I've gotten us to cells. So I've also told you that a cell is a Kantian whole. But Kantian holes can form nested sets. A Kantian hole can be inside of another Kantian hole, can be inside of another Kantian hole. And part of how life has evolved is exactly that. You are made of what are called eukaryotic cells. Bacteria are not eukaryotic cells. A long time ago, one bacterium took in a second bacterium, and instead of eating it, it made the second bacterium symbiotically part of the cell, and plastids arose that can do photosynthesis. Another bacterium got into a cell, and it wasn't destroyed, and the two have co-evolved together. Those are the mitochondria in your cells that make energy. And mitochondria have their own DNA, and so do plastids, and their code's just a little bit different. Well, the mitochondrion is a Kantian hole, the plastid is a Kantian hole, and the eukaryotic cell is a Kantian hole, and you are too. You are made of on the order of 2 to the 50th, 10 to the 20 to 10 to the 30th cells, and those cells form different kinds of tissues and organs like hearts and kidneys, and you are a Kantian hole that carries along by your propagation with children hearts that exist in the non-ergodic universe. So Kantian holes can nest into one or the other, and we do. The next thing I want to tell you about, and it's amazing, and it's developmental biology. So just a story about myself. I was at Oxford, I was going to become a philosopher, and I had a discussion with myself one day. I said, in order to be a philosopher, you have to be as smart as Immanuel Kant. I said to myself, I'm not as smart as Immanuel Kant, therefore I will become a doctor. I couldn't even master the syllogism. On my way to medical school, I took a course in embryology, and a flatworm is this tiny worm. They're pretty adorable, and the experiment consists in taking a flatworm and cutting it in half and waiting to see if it says ouch. The amazing thing is that after you cut the flatworm in half, about a day and a half later, the front half has regrown a back half, and the back half has regrown a front half. And if you look at that and you're not astonished, look again, it's just astonishing. Which brings us to autogeny invertebrates. So everybody seeing this started as a fertilized egg. That egg divides about 50 times to make 2 to the 50th or 10 to the 15th cells, and the cells become different from one another. You have liver cells and kidney cells and spleen cells, about 300 kinds of cell types. So I want to just quickly set the problem for you when I came into biology from being a philosopher. It was known that every cell in your body has the same set of genes. But liver cells are different from kidney cells. White cells make antibody molecules and red cells make hemoglobin. And the puzzle was, how can it be the case that with the same set of genes, different cells make different proteins? That was answered by brilliant work in 1961 by Jacob and Monod, for which they got the Nobel Prize. And they showed that one gene could make a protein, and the protein could sit down next to a second gene, bind to the DNA next to a second gene, and shut it off so that it couldn't make its protein. So genes can turn one another on or off. And 2 years later, they published a seminal paper. They said, imagine two genes, and gene 1 shuts off gene 2. So A shuts off B, and B shuts off A. They mutually repress one another. And Jacob and Monod said, look, this little genetic circuit can have two steady states, A on, B off, and B on, A off. Therefore, the same set of genes can show different patterns of gene expression. And they fundamentally solved the problem, conceptually, of what's called cell differentiation. I will just briefly tell you that I came into biology at that point, and I didn't know any differential equations, but I knew logic. And so I invented something called random Boolean nets. What I wondered was, if you have 20,000 genes, and I treat each gene as if it were a light bulb that can be on or off, and each gene can regulate and be regulated by some other genes, by some rule, which I'll get to, what will this whole system do? Does it take a magic something in evolution and selection to get a genome that can control ontogeny? Or is there order for free in some sense? And I hope so. So here's what a random Boolean net is. There's 10,000 light bulbs, and I connect each light bulb to have inputs from, at random, say, 2 other light bulbs. So it's some wiring diagram, but I've done it at random, and it's fixed once I've done it. And I assign to each light bulb some rule that says when it turns on and off. Like one rule is OR. If C has inputs from A and B, then if either A is on now or B is on now, or they're both on, at the next moment C turns on. That's the OR function. If they're both off, A and B are both off, it doesn't turn on. Another function is AND. A and B are inputs to C, and if they're both on, both A and B is on, then C turns on at the next moment. If either one or both of them are off, it doesn't. So it turns out that there's a specific number of these Boolean functions for any number of inputs, 2 inputs, for example. There's 16 Boolean functions and so on. And I discovered something quite amazing when I was 25. If you take a network with 10,000 light bulbs, the possible patterns of activity are 2 times 2, 10,000 times, which is 2 to the 10,000, which is vastly more than the number of particles in the universe. And you make a network with only 2 inputs, it settles down, and it goes around a small little orbit, what is the analog or an attractor that Jacques Monod had of A on and B off. It settles down to a more or less steady state with about 10,000, about 30 or 40 states on it. It localizes its behavior to a tiny, tiny region of its state space. So what I thought at the time, and I'm just going to tell it to you a bit more, is that different cell types are different patterns of activity of this network. They're called attractors. And it's turning out that that is probably right. Cell types are alternative patterns of attraction to these networks. Then it's turned out after all of these years that such networks could be in 3 regimes: ordered, critical, or chaotic, where critical is kind of the edge of chaos. It's very beautiful. Many of us have worked on it. And it's turning out that genetic nets, in fact, are critical. That's known to be true in yeast. Well, why does this matter? It matters because Kantian holes interact with their worlds in part because they have their own internal dynamics, partly because different attractors are ways of storing different information. I could do this or that. I can also make structures that are memories. So a combination of different attractors and or different structures have memory. And it's turning out that critical networks maximize the correlation between the light bulbs twinkling on and off. It's called mutual information. And it's a very beautiful field that's emerged, which I will come back to. Okay, so now we've got this giving rise, we hope in ontogeny, to your 300 cell types. It turns out that if you take the square root of about 50,000, you get something like a few hundred attractors, which is pretty close to the number of your cell types. And a strange implication that the number of attractors should scale, the logarithm of the number of cell types should scale as the logarithm of the number of genes. And it does. So a lot about this is very hopeful. So this is what I would like to think of as self-organization or order for free. Where are we? That if we make a Kantian whole, and any one thing doesn't affect any other thing in too many ways, namely there's a molecular specificity, we will probably get dynamical order as well. Fine. And we've got the idea of nested Kantian wholes, but we haven't said how a Kantian whole interacts with other things in its worlds. Okay, so I now want to get to the notion of affordances. It's a lovely notion. So here it is. Your sofa affords you a place to sit. Affordances were defined by a psychologist named Gibson some years ago. They're going to be central to what we talk about. We really do sit on sofas. The world is full of affordances. So the next steps I want to take are very strange. Until I say them, I hope it starts to make sense. Affordances are roughly features of the world or other things that are useful to me. The chair affords me a place to sit. I mentioned in the last time I talked that I'm a bacteria and so are you, and your flat surface affords me a surface on which I can go to get food, and I can secrete some glucose on you that affords you a place to to stay alive. So let me state what seems to be very mysterious. In physics, we know what the critical variables are. They're the position and momenta of the end particles in their phase space. In quantum mechanics, it's the energy levels of bound electrons and wavelengths and photons and quarks and gluons and so on. We can pre-state the relevant variables. What we're going to see is that in biology, what I will call biological degrees of freedom are completely arbitrary with respect to the physical degrees of freedom. Let me jump and show us this before we go back and try to get there. There are, as you know, butterflies. Some butterflies taste terrible, some taste good. The butterflies evolve spots on their wings. The spots are arbitrary features. The good-tasting butterflies evolve spots on their wings that look like and mimic the spots on the wings of the bad-tasting butterfly. So the birds will think of the good-tasting butterflies that they should not eat the good-tasting butterflies. That really happens, known as biological mimicry. How do we get to spots and spots mimicking spots to fool birds? But that's all happened. These are affordances, and an affordance is what Calavi-Cull and others call biosemiotics. It's a pattern signaling among organisms. We're going to get there because Calavi talks about a community of species that self-consistently mutually signals itself and coheres in some way that works. So how did that happen? I'm going to get here in a kind of amusing way. My colleague Andrea Rolli, who makes robots, and I have been talking, and Andrea says, you know, when I build a robot, I'm cheating. I put the television camera on its head, and I plug it in and I give it motors so it can turn its wheels. By doing so, I am pre-specifying what can possibly be relevant to the robot. It's light and how it moves. I've pre-specified everything, and I've pre-specified what is good for the robot because I programmed the robot to run around the room, sweep the room up, and then go plug itself in to the power plug and recharge itself. And robots evolved to do that. He said, but I'm cheating all the time. Meanwhile, in robotics, there's an enormous debate about whether or not there's a difference between an embodied robot that's a physical thing or just something on a computer. And we're going to see that there's an enormous difference, and people do robotics. I hope that you will see if you agree with me. So let's take an actual robot, and its outside surface is made out of aluminum. And in the course of sweeping the room, it bumps into something and it gets a dent. For those of you who don't speak English, a dent is a depression in, for example, a metal surface. Well, so what? Well, suppose that there are bumps in the room, and the location of the bumps are correlated with the location of the plug on the floor. If only the poor robot could detect the bumps, and it could use the correlation between where the bumps are on the wall and the floor plug, it could get to the floor plugs faster and quotes, do better. Well, it can't evolve, it's just a robot. Now let's make it a cell that's a contained whole that can actually construct itself. And let's imagine that the cell begins to evolve a teeny bit of a dent, and the teeny bit of a dent is just barely able to detect bumps. Not very well, but well enough. And thereby, the cell can get food faster, so it's selected. Well, it'll get better and better and better and better at detecting bumps. So bump detectors will come to exist in the world. I find this just astonishing, but I haven't told you what a bump is. It might literally be a bump. It might be a dark feature on a wall. It might be a smell. It might be anything or collection of smells and molecules. And the cell can evolve to recognize or detect that feature, which is in general a bump. I've fallen in love with the word bump. It is arbitrary. The bump is arbitrary with respect to the underlying physical degrees of freedom. Well, that's nice. So we can imagine this thing developing all kinds of bump detectors for different kinds of bumps in the world. With that, its world, what it can, quotes, not yet conscious, but what it can know, is is growing proportional to something like the number of kinds of bumps it can detect. Well, that's happening. Now let's have two kinds of robots, or a population of two kinds of robots that are really cells that can evolve. And let's imagine that I begin to develop a dent that can detect your bumps. And you begin to develop a dent detector. So you begin to evolve bumps. I begin to evolve dents. I begin to evolve bump detectors, and you begin to evolve dent detectors to get better and better and better. If by doing so, you and I can coordinate and get to the food faster, to the plug, to the sugar, if we're cooperating with one another, we will pull out of, roughly speaking, a continuum of whatever, specific things like bumps and bump detectors and dent detectors, and they really will come to existence in the biosphere. I just find this astonishing, but think about it. Of course it does. And the bump might be an antenna. On the back of a clam, it might be armature on the back of the clam that tries to ward off the starfish. So if cooperation is in general more important than competition, we will evolve mutually consistent bumps and dents. But the bumps and dents are arbitrary. They could be anything. They could be the spot on the butterfly's wing and the spot on the mimicking butterfly's wing to fool the bird. This is the birth of biosemiotics. It is how cells signal one another and organisms signal one another, and it's mutually meaningful. The bumps and dents are affordances that can be used by one another to coordinate our behavior. The biosphere is rich with the evolution of affordances that are meaningful to everybody around. Your flat surface really is something I can crawl on, and if I'm a bird, those twigs are something of which I can make a nest. And we think the universe is meaningless? The evolution of life is the evolution of myriad meanings. So now we are to biosemiotics. And again, Kalavikal and people doing biosemiotics like von Uexküll and others talk about the Umwelt, the surrounding world of a Kantian whole. They don't say Kantian whole. The Umwelt is me and my environment. But my environment can't be specifically defined. There's no non-circular way to define my environment or my niche. That's only definable with respect to me. And here's the way that I can understand it. The same thing is happening when I go into business and I'm going to make mops and sell them. So if you don't know what mops are, they're what you scrub the floor. I begin by making white mops, and nobody buys my white mops. So I make red mops, and nobody buys my red mops. Then I make blue mops, and nobody buys them. Then I make red and blue striped mops, and nobody buys them. And I try red, white, and blue striped mops, and people start buying it. I have found my market niche. My market niche is what I make that others will buy. Well, that's the same thing that's going on in the biosphere. There is no non-circular definition of the organism and its niche without the organism in it making its way in its world in some mutually self-consistent way. So picture now the evolution of myriad organisms. Some things like your eukaryotic cell have Kantian holes inside them. You do too. You have a microbial community of hundreds of kinds of bacteria in you. The term for this is holobionts. The bacteria in you plus you, they're Kantian holes. You're a Kantian hole. Together you are a nested Kantian hole, a holobiont. And the bacteria in you are doing marvelous things for you managing to be alive. And for example, cows have bacteria in their stomach, or whatever it's called, that can break down cellulose. Without the bacteria, the cow couldn't eat cellulose. So now we are up to magic. We are up to the co-construction of systems with multiple cell types of Kantian holes that make their worlds with one another and make species with one another in a self-consistent way. It's always self-consistent. It's always a constraint closure that transforms to a new constraint closure that may, in fact, get rid of old constraint closures, but it's always a self-consistent becoming. I may have mentioned the TAP process to you, but if not, I will now. About 3 years ago, I wondered if one could write down an equation for the number of goods in an economy next year, given that there's 30 goods in the economy now. So call the 30 goods in the economy now M at time t. So M is 30 at time t, t is now. And what I thought was, and this is pretty naive, if you had that in the next period, say next year, you'd have the M things, the 30 things that worked, and you could try to make new things out of the 30 things. You could try any one thing to make something new. You could try any pair of things, any triplet of things, any quadruplet of things. Well, is this crazy? Well, no, so let's think about it. The printing press, Gutenberg's printing press, is a combination of two things. It's a wine press and movable type. The Wright brothers airplane is a combination of four things. It's a light gas engine, a propeller, an airfoil, and bicycle wheels. We make things by combining things we've got all the time. We can also take a single thing and change it. For example, I know from Roger Koppel, if you look at the axe that we have now and look at its evolution from about 300 years ago, it's the same thing, but it's shaped in a different way. We refashion it. So the equation that I wrote down, and I can tell you the idea, you just think, I've got M things at time t. In the next period, I'll have the M things that I had at time t, and I can try to make things out of one thing, two things, three things. Then the central ideas are easy. It's easier to make something new out of one thing. It's a little bit harder to make things out of two things. It's a little bit harder to make things out of three things, and so on. But consider if you've got 40 things, how many single things can you take out of 40? Well, the answer is 40. How many pairs of things can you take out of 40? Well, it's 2, and all the pairs you can make. Well, that turns out to be much larger. It's 40 factorial, 40 times 20, 39 down to 1, 40, 39, divided by 2 factorial times 38 factorial. So the number of subsets of things explodes until you're taking about half the things, picking all 20 things out of 40 things, and then it goes back down. So what this equation does is it says, it's harder and harder and harder to use more and more things, but there's an awful lot of subsets of things. Apparently this equation is new, and I call it the theory of the adjacent possible, or TAP. We now know about it the following. If I start 20,000 years ago with around 10 things or 30 things, well, and I just evolve it forward in time, the number of things stays pretty much the same or goes up very slowly, then all of a sudden it explodes upward. In a hockey stick, it does that. That's because the more things you got, the more things you can make out of what you've got, because there's so many ways of fiddling them together. And it's really quite inexorable. I showed this to my colleague Roger Koppel a few years ago, and he said, that looks like the Industrial Revolution. So we have looked at it, and it is. It is the case that global GDP has been stable probably for the last 300,000 years at something like $400 per person a year in constant dollars of 1997 or something. It goes up a little bit around the time of Christ, and it exploded upward about 200 or 300 years ago in the Industrial Revolution. Our bet is the Industrial Revolution is an expression of the ease of making new things out of what you've got. So one main point is the following. We are now in the Anthropocene. We're destroying the planet. This is the major issue we confront as a species, and the fundamental reason that we're in the Anthropocene, where we are lifting millions from poverty with our 100 trillion global economy, where we're linking our nations in trade, where we're finding our meaning in our economy, where death rates are going down and literacy is going up, the same global economy growing at 3% a year is now driving climate change, it's driving a mass extinction event, and the wave after wave of pandemics now among us with COVID-19. And the fundamental reason is the explosion of TAP, which goes up like that. And let me bring it home to you. We were presumably as smart 50,000 years ago as we are now. Some people may date it, but let's doubt it, but let's say so. The pace of technological change was very slow 50,000 years ago. it's going faster and faster and faster, presumably due to the tap process. Here's evidence. My father was born in 1903. That's the year we invented the airplane. My son was born 66 years later, the year we landed on the moon. In 66 years, we got from no flight to landing on the moon by an entirely different technology. The rate of technological innovation is exploding. The future is rushing at us faster and faster and faster. The tap process is leading us to overwhelm the planet with our species, where we are on the order of 10 billion. An abundant mammalian species maybe has 1 million or 2 members. There's 10,000 of us to every member of the other species. We are occupying, we're using 40% of terrestrial landmass to grow our food. We are more than 40% of the terrestrial biomass. We and our cows and pigs and sorghum and rice are more biomass than all the chipmunks and crows around. If you think about that, our species is so grotesquely out of balance on this planet. We're overwhelming the biosphere because we're so inventive. Nobody's being bad in all of this. We are being brilliant us, doing brilliant things over 300,000 years, from making wonderful stone tools to penicillin. And we're full of avarice and other things. We're overwhelming the planet. I will come back to this right at the end, but this species, our species, confronts a challenge which I believe is civilizational in scale. This is first world civilization. It's global in scale, and it's existential. We have a few decades to understand how we will live on the world of nature, not above nature. And all that we're talking about is understanding that we're of nature. We have to figure out how to do it. So here's this process in which the number of things increases slowly, then it explodes. I want to interpret the same little equation to say that m at time t, instead of being the number of things at time t, is the most complex thing at time t. So if m is 10, the most complex thing has 10 parts. If m is 1,000 at time t, the most complex thing has 1,000 parts, roughly. Well, this makes sense. You cannot make a crossbow till you've made a bow. You cannot make a space station till you've made a rocket. So the same process is saying over time you get a slow increase in the number of things, and then the slow diversification into simpler and more complex things. Well, that happened. 3.5 million years ago, when Australopithecus came along and started making stone tools, Australopithecus had maybe 10 crude stone tools. By the time you get to humans, Cro-Magnon maybe had a couple of hundred kinds of stone tools. They're exquisite, and they range in complexity from fishhooks and arrowheads to the atlatl, which is a little bit like a lacrosse stick for throwing arrows, and all kinds of complicated things. By the time you get to Mesopotamia, 4,000 years ago, you've got simple things like needles and complex things like chariots and farming and agriculture and a hierarchical society. How many kinds of things are in the economy now? And the answer is billions of kinds of things. How did that happen? And they range in complexity now from arrowheads and needles to the space station. It's the tap process building increasing numbers and increasingly diverse, simple and complex things. There seems to be something fundamentally right about tap in technological evolution. It may apply in the evolution of life from simple to increasingly complex. Protocells, prokaryotes and archaea, eukaryotes proliferating for 2 billion years, then exploding into multicell organisms 700 million years ago, then the Cambrian explosion making really complex things for the first time, leading to T-Rex and us and oysters and redwood trees. TAP may be seriously related to the evolution of the biosphere, and it may be related to the evolution of the chemical diversity of the universe. So there's something going on with this TAP process, and what it does is it starts with a few things and it explodes into diversity over time. But the exploding into diversity is just what's happening in the universe, in the biosphere, and in the technosphere. So this led me some years ago to wonder, is there something like a fourth law of thermodynamics? Let me try to tell you the intuition. We noted that the universe is not ergodic with respect to complex things. Let me define the adjacent possible, which I've done before. The adjacent possible is what can come to exist next, given what's actual now. So in the non-ergodic universe, living things now can give rise to the next things that can come into existence, given that we're here. In the economy, it's the same thing. Given what's actual now, new things can come to exist. They're the complements and substitutes of things that exist now. So once there's cell phones, complements are things that can be used with something. Once there are cell phones, apps that can be used on cell phones come into existence. Apps on cell phones could not come into existence 200 years ago. There was no cell phones. Once there's television sets, television changers could come in. What you need for that are televisions with more than one station and couch potatoes, which I am at 80. So what's happening in the evolution of the biosphere, non-ergodic, and in our economy is what exists now enables what comes to exist next. It doesn't cause it, it makes it possible. So this, a number of years ago, made me wonder the following. Think of the adjacent possible in the biosphere. It's what can arise next. Compare that something like 3 billion years ago to now. Well, what can happen next 3 billion years ago is a lot less than it is now. So the adjacent possible seems to be getting larger. Well, TAP does the same thing, and it may be either a real explanation of it or a model of it. The more things that are around now, the more things can be made out of them next. So I've been thinking for years that there's something anti-entropic about something like an expanding adjacent possible, which is going to take me back to the paper that I'm writing with Lee Smolin and Marina Cortez and Andrew Little. Lee is now framing it quite beautifully, and you can see it in TAP. So this TAP equation happens to have a parameter in it called alpha, which is the likelihood that you can use things with I parts. So it's alpha raised to the ith power. And it's just supposed to say how making things gets harder and harder and harder as you're trying it with more things. So if alpha is equal to 1 in this equation, you keep being able to make everything. It's just this thing in this equation. So in that case, what TAP does is it just explodes incredibly fast. If alpha is less than 1, say a half, what the little equation says is that alpha is equal to half for one thing, and a half times a half for trying to do two things, and a half times a half and a half for three things. It's getting harder and harder to do more things. What that does is it narrows down, in this TAP process, it narrows down the things that actually can get made compared to what could have if alpha were 1. So it sounds a little mathematical, but here's the idea. The TAP equation exhibits the following. This parameter alpha is 1. It makes everything possible. If alpha is less than 1, it makes a subset of what's possible. So let me say it again so you get it. The equation is alpha to the ith power times whatever you're looking at, the number of ways you can make a subset of I, size I, out of empty things. So to be concrete, if MT is 40 and I is 2, you're asking about all the possible pairs of things that you can take out of 40. And if alpha is a half, then the probability that any one of these pairs works is a half times a half, which is a fourth. Any 3, you're taking 3 things out of 40, but the chance that you can do something with it is a half times a half times a half. It's an eighth. So it's getting harder and harder to make things out of bigger subsets. What happens is the total set of possibilities that it can arise increases in time. Call that the total possibilities. The actualized possibilities are smaller than that. The actualized possibilities are increasing in time also, but it's smaller than what could have happened. In other words, what actually comes to exist is a subset of what could have come to exist. That's exactly what's happening in the biosphere. The actual biosphere that comes to exist with lions and tigers is some tiny subset of what might have come to exist given the start of life. Can you feel it? The buildings that come to exist are a tiny subset as we build things of all the buildings we could have built. So the idea is the following. In the numerator on top, look at the total possibilities, TP, and divide it by the actualized possibilities. So it's TP over TA, total possibilities over actualized possibilities, and call that R. R is the ratio of what could have happened to what did happen. And the statement is, over time, all of these tend to increase. The total possibilities increase, the actualized possibilities increase, but the actualized possibilities are increasing more slowly than all of the total possibilities, so the ratio of them, total possibilities divided by actual possibilities, is also increasing. We think that's a fourth law of thermodynamics. We think it's true in the non-ergodic universe, and we think it's a companion to the first three laws of thermodynamics. So now let's look at where we've gotten. The universe becomes more complex, making simple and complex molecules. Life starts, it can build itself, it can build its own boundary conditions. It can now create things that have never existed before, and it constructs itself into the adjacent possible that it itself creates. We are creating the conditions for the next goods and services that will enter the economy, and we don't know what they can be. It's not prestatable. There's something like a fourth law in which the universe is getting more and more and more and more complex, where the ratio of what could have happened divided by what did happen is getting bigger and bigger and bigger, and that's probably roughly true. I want to get to a final topic. What's information? So we know Shannon, and Shannon in 1948 said he was concerned with propagating information down a telephone line. And he said, let's represent information by ones and zeros. Well, what's a one and what's a zero? It's the presence or absence of something, for example. So it's the presence or absence of a bump. And there's myriad kinds of bumps. So information is a representation of all the kinds of bumps that are present or absent now, which is some very long string of ones and zeros. Pause. Let's name all these bumps. Bump, dibbly-dorp, glop-glop. So I've got names for all of these things. And now the statement, bump present or absent, bump present is true or false. The dibbly-dorp present or absence is true and false. So I'm now referring to bumps with the ones and zeros. The ones and zeros aren't the bump. There's some representation of it. What Shannon tells us is we start with some information, namely we should start with a source of information, and it consists in strings of bits, length n. So if n is 1,000, one string is 10111001, whatever it is. And so I have bit strings all length n. The n could be 2 or 10 or 100. And there are therefore 2 to the n possible bit strings. Think of each one as a message. So make n 10. So there's 1,024. And in the source, some of the bit strings are present often and some aren't present very often. So I can define the entropy of the source, and it's the logarithm of the number of copies of each kind of message. So it's some p log p, and it's exactly the same as Shannon's. Shannon's entropy, Shannon's information is minus Boltzmann's entropy. And it sounds really important, and it is. So what Shannon then says is pass the signal down the channel. You can't create any information, it's what you started with, but you can sure lose it. It could be a noisy channel. How do you keep yourself from losing the information going down the channel? Well, you invent error correcting codes and so on. So for example, instead of sending 1 bit, you send 3 bits. So 1 is captured by 111, and 0 is captured by 000. And if at the receiving end you get 110, you say it must have been 111. So it's an error correcting code, and there's an enormous amount of work on it. Notice that Shannon information, A, cannot be created, but it can be destroyed. And it is syntactic. There's no semantics. We don't know what the ones and zeros mean. We're propagating information down the channel. And again, there's no creation of information. And a 1 stands for the presence or absence of a bump. But the bump is a real physical thing. The evolution of the biosphere in this fluorescent becoming of bumps and grooves and dents and dent detectors and so on is precisely the generation of meaning. It's therefore the generation of semantics, not syntax. There's no syntax. Okay? When the amoeba makes its way in the world, there's no syntax. The amoeba has bumps and dents and whatever, and it's making its way in the world. It is not a computation using bits. It's the amoeba making its way in the world. And the same thing for a plant, and the same thing presumably for a starfish, and the same thing for us. So it's really important to distinguish the generation of information, which life does, and the transmission of information with bits, which a computer does, and a quite different communication of information in biosemiotics. So I'm almost going to finish with the following problem. It's called the frame problem, and it's never been solved in good old-fashioned AI. So the frame problem is the following. You go in to get dinner, and you know what the frame is. You're supposed to order dinner off the whatever, the menu. In a funny environment, good old-fashioned AI cannot figure out what the appropriate context is. It's because it's operating with bits and doing a computation with bits. Once you have the robot and it's actually physically embodied in an aluminum structure that can get a dent that now is able to detect a bump, detecting a bump is good enough or bad enough. It works or it doesn't work. It's not a bit that's true or false. So the embodied robot or the embodied cells solve the frame problem all the time. We cannot do it with a computer. And among other things, this is the difference between AI, artificial intelligence, and us. Artificial intelligence can't get meaning, and we can, although we can try. So that's debatable. So let me now truly finish with where we are. We started with 10,000 years ago with Kalevala and the sense of awe in which the old women squatted around the flames say, Kullervo cut down all the trees with the bare knife of Kullervo and left one tree left. Its berries become all that is. There's this sense unstated of an explosive potentiality in the berry that becomes all of life. And we are situated, we with the berry, we are of nature. 7,000 years later, Homer is telling us about why Odysseus and his ship got sunk in the wine dark sea. It's always wine dark, which is pretty neat. And we know the answer because he told us. It's that Odysseus' men had the poor taste and stupidity to steal the cows of the sun god, Helios, who goes to one of the other immortals, Zeus, and says, I am really angry about this stealing of my cows. And Zeus says, you're right, Helios, shine on. I am going to get these mortals. And he arranges to go and hide in a cloud, and he heaves a hideous thunderbolt, and it destroys the ship, and the mast comes crashing down on the helmsman, whose bones break and his life is gone, and everybody dumps into the sea and dies. So 3,000 years ago, or 3,500 years ago, in the time of the Trojan War, we were embedded in nature and talked to the gods and argued with the gods and prayed to the gods. And the creativity was in chaos, eros, and the order was in the heavens of the stars rotating around. And chaos is the source of all the creativity. And the Hebraic God becomes Yahweh. And after all, Moses argues with Yahweh, and Yahweh gives them the Ten Commandments, and they argue on Mount Sinai. So we talk to the gods occasionally. Well, along comes Thales, or Thales, and says, it's not the gods. It's a substance. It's water, which you can't pray to. It's just water. Then it becomes, look, reality really is earth, air, fire, and water. So now we have quarks and gluons and pions and stuff. It's the same idea. And then that becomes Democritus and the atoms in the void. And reality becomes the atoms in the void bouncing deterministically off of one another. We can't pray to the atoms in the void. The old Greeks keep Zeus, and they have Athena, and they have temples to Athena, and so on. Then we get the Judaic God and the Christian God, who becomes ever more abstract. He's all-loving, omniscient, omnipotent, and God is the source and the intelligence of all the creation. How could it possibly be true, unless God created it in 7 days or 6 days, that all of this miracle would exist around us of cows and pigs and raccoons? And so says the Jewish Bible in Genesis. The intelligence is out there. It's beyond the stars. It's in the entelechy. It's in the intelligences that the 14th and 15th century people studying the Kabbalah can bring down by rubbing stones together and bringing down the intelligences through into the material world and be called forth by rubbing the stones together. But the creativity is out there in the heavens. Gets us to Copernicus, who destroys the conception of the cosmos of the Christian church, of the Catholic Church, gets us to Newton, who invents differential and integral calculus, 3 laws of motion, and universal gravitation, and the whole world is now not chaos, it's logos, it's all law, it's all mathematical. And Pythagoras was right. Becomes also quantum mechanics, both within the Newtonian framework of entailing laws. Down there are the laws that, not to pick on Steven Weinberg, he's an amazing scientist, but the dream is there are laws down there that unite general relativity and quantum mechanics that will allow us to derive everything that will happen in the universe, which is meaningless, said the existentialists, and we must find meaning somehow in our own choices, but it's not clear how those happen. And it's Weinberg seriously saying, and I don't mean to pick on him, he's a superb scientist, the more we know of the universe, the more meaningless it appears, which entirely ignores life. So life comes forth plausibly because the universe cooks up an increasing diversity of molecules, simple and complex. So by 5 billion years ago, we have thousands and thousands of kinds of organic molecules in the same spray that Albrecht Ott can make, with the hope that that gives rise rather readily to molecular reproduction everywhere in the universe, with 10 to the 22 possible solar systems, to molecular reproduction that goes from small molecule to polymeric to living things inside of something like liposomes, to maybe template replication and coding, to biospheres all over the universe, where Kantian holds that construct themselves, break free of Newton, and can go into the adjacent possible that they construct for themselves, maybe all over the universe, making meaningful worlds in which they exist. The name of this whole thing that I've given to it is to come home again and recognize it anew. Maybe this is precisely that. It is coming home again with Kalevala and recognizing that from the berries comes everything. Well, from the berries does not come quarks, but from the berries alive come all that is in all the biospheres in the universe, for which there's no law. We are at home in magic and law. We are at home in story and law. And I feel like, to me, that's another homecoming, and we are in the world in a different way. We confront the Anthropocene that we've created. If we can find in any means, but including this which I'm saying, a renewal of wonder, it's the same wonder that's there in Kalevala, all comes forth from the berry, then we can become of nature, not above nature, and hopefully find a way of surviving on this planet before we destroy the biosphere. We have a couple decades. It's a massive issue, but we're pretty smart, and actually we are capable of love. So let's hope that we do it. Hello, my name is Stuart Kauffman. It is mid-August 2020. I'm going to be talking for several hours, and we're going to record it under the tentative title, To Come Home Again and Recognize It Anew. This, however, is a piece of a much larger effort. Some 15 of us, scientists all, and some marvelous production people are joining force, hoping to create a multi-part TV series whose title, we hope, is The Shape of History. Its aim is to start at the origin of the universe, explore that, the origin and evolution of life, the origin of the hominid lineage leading to us, our technological evolution, now reaching into the Anthropocene. The Anthropocene is us. After 300,000 years on this planet, our own brilliance, building an economy of 100 trillion a year, growing at 3%, has lifted millions from poverty, is increasing lifespan, is linking our nations in trade, but it is also causing climate change, a mass extinction, and wave after wave of pandemics. We confront, and this is the reason this group of us is coming together, a challenge that is civilizational in scale, it's global in scale, and it's existential. We have perhaps 1 or 2 decades to try to understand how we will live on this planet in some kind of sustainable way. To tell you a bit about the 10 or 15 scholars, it includes cosmologists, quantum physicists who have invented one of the best ways of trying to think about quantum gravity, a number of people who've thought about the origin of life with possible experimental approaches and radically wonderful new data and ideas, experts on hominid evolution, trade, Pleistocene, and technological and cultural evolution, which we will explore. What I will talk about in the next while are my own efforts to see what is happening. To borrow an exquisite line from Yeats, what rough beast, its hour come round at last, slouches towards Bethlehem to be born. The group of us, and I think others, sense some rough beast is slouching to wherever Bethlehem is to be born. We sense something of its shape, something of its humor, something of its smile, something of its laughter. We are hoping that it hovers in a morning fog more closely into view. We hope we're able to bring it to you as we understand it and others are understanding it. What you will hear from me is my particular effort among many superb colleagues. So once again, we are in the Anthropocene. The Anthropocene means humans' impact on the biosphere. I've already said it, but I'll state it again. Our global economy is a juggernaut. It is growing and growing and growing. It's been 3% a year until COVID. It really is lifting millions from poverty. It is unequally distributed, causing anguish around the world. It really is driving climate change, ocean acidification, ocean rising, the bleaching of corals. It really is driving a mass extinction where we expect that in something like 30 years, a million species, something like 20% of the standing diversity, will be extinct. Think about it. It's taken 3.7 billion years for the accumulated know-how of organisms making their worlds with one another to come into existence. And what makes us think that this extinction event will only be 20% of the standing diversity? The largest extinction event was the Permian, 255 million years ago. 95% of all species went extinct. We have no idea how large this is going to be. And we are driving, in fact, wave after wave after wave of pandemics. SARS, Ebola, and now COVID. We're invading habitats all over the planet. We are doing it. We are causing it. This is us. And we're not being malicious. Some people are. Some people are interested only in profit. Mostly, this is the culmination of our own human creativity. It is, in fact, the natural process of TAP itself. My friend Roger Koppel, one of our groups, says, technology is happening to us. Kevin Kelly wrote a book called What Technology Wants. We do the next thing that we're invited to do by where the economy is now. It really is true that the challenges are global in scale, civilizational scale. This is first world civilization. They really are existential. What I want to do before we really start is, in a way, to tell you a teeny bit about myself. 3 years ago, I wrote down the TAP equation. It's the only equation I've written down, and you can see it here on the screen. Here's what it says. M sub T is the number of goods in an economy, number of types of goods in an economy at time T. It could be goods, it could be tools, it could just be things. And what I was thinking is, if there's M goods at time T, how many will there be in the next period, T plus 1? And the idea is just so simple. It says, as I've told you, if you have MT things, say 40 things now that work, carry them forward with you. They worked. And why not try to make new things out of the 40 things you've got? So try one thing to fiddle around with at a time, or any pair of things out of 40, or any triplet of things out of 40, and so on. This seems to be a new equation, and it may be very fundamental. What it does, and I've told it to you, but I'm going to show it to you, is if you start with, say, 10 things and run the process forward, it stays 10 or 11 or 12 for a very long time, and then it explodes upward. Faster than exponential, it's called hyperbolic. It reaches infinity, goes all the way up in the continuous version at some finite time. Roger Koppel, my colleague, who's an economist of the Austrian school, looked at this several years ago and he said, that looks like the Industrial Revolution. Well, indeed it does. The next slide, or the next figure rather, shows you global gross domestic product for the last 2,000 years. I find it stunning. Global GDP stayed roughly constant at about $400 per capita for almost 2,000 years. We think we can stretch it back 20,000 years. The bet is that hunter-gatherers were living at the same level as people in the south of France in the year 500. And then it explodes upwards in the Industrial Revolution. And here's why it explodes upward. The more things you've got to try to make things out of, the more ways there are to do it, and it just gets easier to do it. And one intuition is the following. Suppose you've got something wrong in your house and you've got to go fix it. You've got to tinker together a solution. Would you rather go to the garage and find one thing, a broken rake, or a few hundred things? Well, it's easier to find a few hundred things and fiddle them together to solve the problem. Fiddling together is jury-rigging. It's easier to jury-rig with 100 things than with one thing, and that's why this explosion happens. It's the danger, it's the catastrophe we face. I think it may be the hope for the future as well. We can be so stunningly creative, we may find a way to use the TAP process, which will happen anyway. So the final thing I will show you here is the TAP equation, and showing you that it fits the data for the growth of GDP for the past 2,000 years. Roger points out something fundamental. Because in TAP, the diversity of things increases so slowly, for thousands and thousands and thousands, maybe 300,000 years, every time GDP went up a little bit, Per capita GDP went up a little bit. The population increased a little bit. Per capita GDP went back down because population went up, and people died. We were in the Malthusian trap for hundreds of thousands of years. Then what happened, Koppel pointed out to me, is the tap process kicked in and it started exploding. When it did, per capita GDP rose faster than population could. Population started to explode, and it has done so for the last 150 years. Now there are 7.7 billion of us. We are post-Malthusian trap. We may be entering into what a colleague of mine calls the final Malthusian trap when we overwhelm the biosphere. Nobody knows what the answer is. I'm going to try some thoughts. However, this is a discussion that needs to take place on a global scale. There are 7.7 billion of us. I'm going to start with a comment made by Gordon Brown, who was Prime Minister of the United Kingdom some years ago. He commented, "We are reduced to price tags." The interesting thing is we all know exactly what Gordon Brown means. We are reduced to price tags. But if I ask the question, reduced from what, we become confused. Somehow, we are reduced from our human center, our human being on this planet. Our center as human beings is not being consumers. It is not making, selling, and buying purple plastic penguins for the poolside. Even if many of us want purple plastic penguins for the poolside, and I, for one, would not want to be a czar saying that cannot exist. But that reflects our value system. Let's think about where perhaps we are coming in this vision, rough beast, as I said earlier, of something new being born. Remember, we started with Kalevala and Kullervo, with the bare knife of Kullervo, who cut all the trees cut, but left one tree, its berries become all that is. Just sit and feel that. The berries become all that is. We were, 10,000 years ago, situated in our world among creation, whatever creation is, and knew it and were in wonder. And you feel it in the line. The berries become all that is. Then we talked about Homer and Odysseus and why his ship sank at sea, because his men had stole the cows of the sun god, who asked Zeus to destroy the ship, and Zeus heaved a thunderbolt. Again, we were situated in a world of people and gods and chaos and creativity and order in the heavens, and we knew our place. We were situated human beings. There's an important sense that I've tried to make as we talk, that as we got to Thales, and water is all, and earth, air, fire, and water is all, and atoms and Democritus is all, and now quarks are all, quarks and gluons, and the elementary particles, we cannot pray to them. We are not personally involved with quarks and gluons any more than we were with water as a substance. If Moses talked to Yahweh on Mount Sinai, we can't talk to particles. And we are, in the view of so famous and superb a physicist Steven Weinberg, in the situation where the more we know of the universe, the more meaningless it appears. But that forgets Kullervo and the berries. We are the berries. We are Kullervo. We are, I think, in the world again in a new way. Maybe not yet. Look where we were in the cosmology of the church for 1,000 years with the spheres of Aristotle with the stars on them, the lower spheres with the moon and the sun, all revolving around the earth, the planets a little bit discordant, God above, the angels, then us, below us, deer, worms, creepy things, down to hell. Everything revolved around humanity. Copernicus came along, Galileo came along and said no, and shattered the worldview that had been there for 1,000 years. In a sense, since wonderful Galileo watched the swinging chandeliers and rolled the balls down the inclined planes and said the world is written in mathematics, as had Pythagoras, we have lived that with stunning Newton, the Newtonian paradigm, quantum mechanics. Then Darwin and evolution. Darwin thought he was the Newton of biology. Immanuel Kant said there will never be a Newton of biology. Kant was right, although Darwin brought us history. And we now begin to see why there is not ever going to be a Newton of biology. So let me say that part again to be utterly clear. Remember, we talked about the engine block out of which your engine is made. And it's about 12 inches or 14 inches long, 10 inches deep, 7 or 8 inches wide. If you will make an engine out of it, you drill holes that will become the cylinders and fashion an engine block. But I did tell you the wonderful story of the invention of the tractor, where one of the engineers said, you know, the engine block is so rigid, we can use the engine block as the chassis. And that is how tractors are made. But then we realized the engine block has corners that are so sharp they can be used to crack a coconut against and open coconuts, which is a little comedic, or as a paperweight. Or if the sides of the chassis were very shiny, it could be used as a mirror. Or if one of the sides was hollowed out concave, it could focus light and start a fire. What that means is two huge things. Evolution is actually made up of actual physical things like proteins and membranes. They are real objects in the world, like the engine block. Each of those has many causal features, and a causal feature of no selective significance in this environment can come to be significant in a different environment. That's Darwin's pre-adaptations. They're all over. We talked about the swim bladder, and it's coming into existence, and new functions come into existence. So we know that. Here's the salient point. Given that the engine block is being used as a chassis, is there any way at all to deduce that the engine block can be used to open coconuts? Is there a deduction that gets us from engine blocks of use as a chassis to their use to open coconuts? I think the answer is obviously no. What would the deduction be? But that coming to be of new uses of physical things in Kantian holes is happening all the time in evolution. The new use is not deducible from the old use. Therefore, there is no theory, which is a deductive entailing theory, for the becoming of the biosphere. And we are in the world in a new way, given that. We will discuss it. We will understand whether we believe it or not, that it's true or not. I think it's obviously true. It means a radical freedom in the becoming of a biosphere. My own sense is this is the rough beast hovering to be born. This is the berries and all that is. We are of it. We are not above it. Feel, please, the know-how that is accumulated over 3.7 billion years in which your flat surface affords me a way to crawl to food while I dribble a little glucose on you if I'm a nice guy. That's 3.7 billion years of a mixed economy of creatures making their livings with one another. Their bumps and dents, bump detectors and dent detectors being arbitrary features that become the spots on the butterfly wings by which it warns the bird that it might taste bad even though it tastes good. This is the biosphere, utterly rife with meaning. We are of it. I feel the awe. I feel the wonder. I think we can all really come to feel the wonder. The creativity need not be in the heavens. The creativity is all of us coming to exist. In this biosphere, there may well be biospheres all over the universe in the 10 to the 22 planets around the universe or solar systems. So we maybe have wonder again. That's fine. Scott Gilbert, one of our groups, says, from wonder comes curiosity, which becomes science. From wonder comes awe, respect, and gratitude, which is religio. But that's not living practically in the world. We have to begin to take on, as a species, 7.7 billion of us, how we will live as a species on this planet. Now, as I mentioned to you, with ourselves and our cows and pigs and sorghum, more than 40% of the terrestrial biomass, using about 40% of the planetary surface to grow our own food. Since the agricultural revolution, we have sucked the planet into making us. And in a sense, we are in a sense a cancer in the biosphere, even when we are loving our children. So let me suggest some possibilities. These are just suggestions. This needs to be a conversation that becomes widespread. And this is one tiny piece of conversation. One thing is to ask, what is GDP? Well, goods flowing in one direction is money flowing in the other direction. So increasing money flowing in that direction is increasing GDP. How do we increase GDP? We sell more goods flowing in one direction, then more money flows in the other direction. We sell new kinds of goods flowing in one direction, and that becomes increased GDP. We also sell goods that wear out rapidly in one direction, so that there's more GDP created by having to sell new goods. I am told, and it may be true, that 10 years ago you could buy batteries that lasted 6 or 8 years. I am told that now our batteries last a year. Well, we have to sell more batteries. So I got an image. It's 40,000 years ago, and we're gathered around the fire with the other Cro-Magnons, and one of the group has brought in an auroch. And we've eaten around 15% of the auroch. And the fellow who brought in the auroch says, it's time to throw it away. It's an old auroch. Let's go hunting and get another auroch. And we would all look at him and say, you got to be kidding. The auroch we've got is perfectly good. We don't have to go hunting for another auroch. Why should we go hunting again? Let's hang out, sing songs, and play with our kids. But that's actually what we're doing. There's pretty good data that we can look into that hunter-gatherers work less hours than we do, and they have a modest standard of living. It's episodic. But one thing that could possibly attract us, and it has to be something we want to live, is what if we made things that lasted a long time? My friend Lars Larsson in Sweden, who should have been born 1,000 years ago, lives on some land his family has had for 1,000 years. Lars has a wooden barn from 500 years ago. Well, if the Swedes could make a barn that lasted 500 years ago, so can we. We'll have to learn from them. What if, as 4 centuries ago, we pass things down to our children and grandchildren? Well, GDP would not grow as fast. People would be out of work. They wouldn't earn as much money. But if they already had the things they needed that lasted several generations, they wouldn't need go and make so much money. They would already have what they need, housing and so on. It's at least a thought. Another obvious thought is a circular economy that doesn't waste things, including we're wasting 20% or so of our food and ruining the planet with plastic. The last thing I'm wondering is just wondering right now. The cause of our problem is our own triumph. It's tap exploding upward in enormous creativity. Is it possible that we can find a way to live on the planet using jujitsu on tap, now that we begin to understand it, to be enormously creative, living flourishing human lives in the Maslow hierarchy, where the top of the hierarchy is self-actualization in your community and meaningfulness, for example, with family and friends, and find ways of being creative that are fulfilling and profoundly good without devastating the planet. Possibly we will have to think. I'm hesitant We are used to and evolved earning our living out in the wild, like tigers and lions, having to eat and forage our way. So for us, part of our evolved sense of meaning is going out in the world and making it. It's not sure how that finds a fulfillment in a future where in some ways practicality is easier. I don't know. None of us knows. So I want to end by saying, presumably we're not smarter than we were 300,000 years ago. We now recognize what we are doing. We may well have come home again and recognize it anew. With that, we recognize and recognize vast opportunities, vast responsibilities. We need to accept the fact that we have a few decades to come to live of nature, not above nature. And we need a global conversation. Thank you.